Good afternoon, everyone. So thank you for coming to the seminar, right, virtually. So today, so I'm Dong Chen, assistant professor in computer science. Today is my great pleasure to introduce to you our invited speaker, Dr. Kevin Desai. He's an assistant professor in practice with the computer science department at the University of Texas at San Antonio, UTSA. He received his PhD and MS degree in computer science from the University of Texas at Dallas in 2019 and 2015, respectively. So he also received his bachelor degree from computer engineering, actually from Nima University from India in 2013. So Dr. Desai's research interests include 3D computer vision, multimedia systems, mixed, virtual, and augmented also reality, also human-computer interaction, machine learning and deep learning-based applications, in particular in the domains of healthcare, virtual training, and serious gaming. So Dr. Desai's work has been published in multiple top-tier conferences, mainly in the fields of multiple media. For instance, MMCs, which is a flagship conference for multimedia data management, also ISM, Big MM, and ICME. He has been serving on multiple like a program committee member and a reviewer for multiple peer-reviewed international journals and conferences in IEEE, ACM, and Springer. So today, Dr. Desai will give us a talk about his recent progress about his research in 3D computer vision, interactive 3D tele-immersion for serious gaming. So now let's welcome Dr. Desai to give us a talk. After his talk, we will have a very short Q&A session at the end to answer your questions. Thank you.
Yeah, thank you so much, Dr. Chen. Yeah, hello everyone. As you mentioned, I am Kevin Desai from UTSA Computer Science Department, and just wanted to just point out, I mean, all of this work, what I'm presenting is not really just completely recent, right? I mean, I've already done this, most of this work has already been done. I'm just presenting it as a, like a complete package in a sense of what I do and what are the different fields that I cover. I know you may have seen a lot of different fields or you may have heard a lot of different fields as you mentioned, but I don't go into details for all of them. I'm kind of working in the, like in the junction as a cross-discipline, like a research and mainly in computer vision, VR, AR, and some multimedia systems. So this was just the teaser slide where I'm showing you all of my, or some of my work in terms of the video and whatever is happening in all of these videos. I'm probably going to start talking about each part of it not in complete detail, obviously just 1 hour, but in fairly enough details that can give you some idea and some perspective. At any point, I would highly encourage if there's any question at any point, and if you want me to cover something or talk about something a little bit more in detail, please feel free to stop me. Rather, that I would encourage that. That would be probably better for more of a discussion at that point. Yeah. So just to start off, as the project or the title suggests, what I generally work with is 3D tele-immersion, right? And more like interactive 3D tele-immersion. So there's two parts that I'm gonna talk about mainly: interactive 3D tele-immersion and then serious games. Right, so they begin with interactive 3D tele-immersion. In a general sense, I mean, there's been different terms which people have used, but I generally stick with the 3D tele-immersion term because that's what I feel is the most widely used term. Sometimes people use mixed reality applications as along with 3D tele-immersion, right? But the general idea is in all of these games you would see, a lot of these things you would see is I'm capturing a person and I'm placing that person, for person. I'm capturing this person in 3D in real time, and I'm placing that person in virtual environments. Right? That's what a general immersive immersion or a 3D tele-immersion scenario is. Now, the first point is, how is that happening, right? So a general idea of the framework which we use, and I think a lot of researchers in this domain, they generally use this kind of a framework. Yeah, so we have a camera. We work with, or I work mainly with the Microsoft Kinect camera, right? So we have the camera, we extract the color and the depth image. From that, we do some processing by extracting the person, doing some filtering, reducing the number of points, creating the mesh in real time, align them all together and create a textured mesh in real time. And that's one part of the work in creating a 3D model. But the other part of the work is actually doing some interaction with the virtual objects, right? So we have this other side of stuff where we use this Kinect skeleton and do some processing. I'm not showing you the processing part, but do some processing, maybe do some improvement, maybe do some use our own skeletal recognition technique on top of color or depth image, or both of them, to extract the 3D skeleton. Yeah. But once we have the 3D skeleton, we assign the colliders and place them in a virtual scene. This is an example. This is a scene for a chemistry lab setup. We can place the person in this particular setup. Yep, so that's the general idea. Now becomes the point of serious games, right? So I know, I mean, games are something that we can focus, right? There can be different kinds of games in the literature. We have just games that we play for fun, like just entertainment and fun, right? But there are some kinds of games where fun is not the main objective. Along with fun, you want to have some actual task that is going on in the background where you are trying to learn something. Those are what are known as serious games, right? So games which are meant for serious objectives, not just fun or entertainment, those are the games that are called serious games. Now this game, Penalty, in some sense, it is just a fun game. But always, we can always portray it as a training game where I'm training the goalkeeper to save goals, or where I'm training the penalty shooter to take penalty, right? Now, as you see, I'm placing this person in real time. Obviously, there's some holes that are coming in from the capture. But for the other person, it's not too much. Maybe it's just about how the camera was, or it's just about how the mesh or the cloth, what the person was wearing, because of how the camera captures the time of flight cameras. So, and if you see this, there's just two persons interacting over here. Now, both of these people, they are present in different locations, right? As if we guys are present right now, I'm present in Dallas, and you guys are present in, I'm present in Texas, you guys are present in Florida. We can still collaborate. We can still have an interactive game where we can play or interact with same, or like virtual objects which are present in the same game, right? So this ball is the object which is being shared in the environment. Yeah. So I can create this setup. So this is the setup that we created, and we work with. This is one game. There's multiple different games that I had focused on. Primarily, the focus was in rehabilitation scenario, right? So the primary use case, which I focused was the rehabilitation and exercises, right? So for that, I created this Exergames toolkit, if you would like to say it that way. It's a toolkit where there's like 4 different games, one assigned to each different exercise. Yeah, so there's this virtual game where the person is seeing themselves in the 3D environment, and the idea is the concept of mirror therapy in a sense, right? So if you see yourself playing a game, you would be motivated to performing or to play or to do something better rather than what you would see or what you would not see yourself, or how you would do by not seeing yourself. That is the general concept of mirror therapy, and the primary focus was stroke affected patients, right? So the whole job is to motivate them to keep on playing and keep on performing an exercise. So as you saw, 4 different exercises and 4 different games. Shot put for elbow, like, or this exercise. There's bowling for this elbow or shoulder extension. There's balance for hip abduction, and then there's rehab quiz kind of a game where there's some cognitive component which is also integrated. Obvious problem with the previous version was I cannot have thousands and thousands of games, right? I can have tons of exercises, and I can have tons of patients having minor variations in those exercises, right? So I just advanced and created this in-home rehabilitation exergame, which is a generic game where if you saw the left part is a recording which is being played, and the right part is the live person being performing this exercise. Yeah, so the therapist, well, in this case it's me, but the therapist is recorded, and that recorded therapist is used to predict these bubble locations based on the skeleton of the person, and they can perform this game. Right, so there's different things going along with it, the game side of it, the capture side of it, the recording side of it, and the prediction of the anomalous movements and recording those anomalous movements. So predicting whether those joints, that the person is correctly doing the exercise or not. And fall is one of the major anomalies that we would like to detect, or that anybody would like to detect whenever people with disabilities, they're performing some exercises. So that was about exercises. Going into the realm of education, right? So you can create chemistry experiments or virtual laboratory settings where the person can play different kinds of, or create different kinds of exercise or experiments, and the student can be trained to perform certain experiments, and as a matter of fact, even be evaluated how they are performing, right? So I need to go down and look at the level of the liquid at the meniscus level rather than looking at it from up high, because I would be getting the wrong measurement if I'm going to look it up from high, right? So it needs to be at the eye level to measure the correct liquid. So all of these things can be evaluated, and we can do some assessment internally as well. Yeah. Another kind of games, or other chemistry games where you have collaborative setup, where you have multiple people. The instructor could be grading how I'm performing the task, or there could be a group of students performing a task simultaneously. Right? So all of this was about the serious games, but there's different things that are involved in it, right? I mean, as you would assume, there's a lot of components that are involved in it. Obviously, there's the interaction component, but apart from interaction, in terms of computer science research and computer vision part of it, the first problem or the first challenge is how do we validate, or how do we quantify whether any mesh or any 3D model that we see is a good 3D model or not, right? And this is a bigger problem in this particular use case, is because most of such applications are going to use one camera, right? You use one camera to capture a person in real time, right? So you're not really creating a complete 3D model beforehand. You're rather creating this in real time. Yeah. So the problem that comes in is what we call the human open mesh, the open mesh problem, right? So this mesh is not really complete. Yeah. So there's missing information from in the back, obviously, but even there's going to be missing information when there's occlusion, or when there is motion, which is being wrong, right? So there's different artifacts that would come in. There's the occlusion, there's rigging, there's segmentation problems, there's skinning problem, there's meshing problem, there's a lot of problems that would come in, right? So how do we quantify, or how do we evaluate how good our mesh generation strategy is? Yeah, so for that aspect, obviously we can do, like subjective feedback, but we would want to integrate that subjective feedback of what user sees into some objective measure. The problem with the known methods or the known strategies was the fact that most of those strategies work with a closed mesh, and most of the mesh evaluation strategies work with watermarking techniques, right? So that the whole idea is, if you have minor variations, you would want to validate how much impact those minor variations have, the watermarking techniques. Yep. Or noise that would be added in. But the general part, or what I'm trying to do, is not really about that. What I would try to do is try to evaluate the overall quality of a human mesh. Yes, it's mainly about that I'm targeting this for human mesh data. Yeah, what I'm doing is I'm just computing a visual quality measure, which is I'm dividing it into two parts. One is the local score, and the other is a holistic score, where we try to evaluate the model as a complete model rather than local part-based stuff. Yeah. So the overall or the holistic score is basically mainly considering the silhouette or the overall erroneous triangles and holes that are present in the body. The local scores, what we try to do is we try to evaluate it from the local parts, right? A simple thing or a simple example is, it is fine if some part of my body, some part of my torso is not being captured properly. But it's not fine if I'm not having high quality face or high quality, like how I'm seeing myself, right? If there are a lot of holes on my face, or there is not a lot of variation on my face, there is not a lot of roughness in my face, that is not going to matter, or that is a problem. It's not going to matter if I have a torso which is just a flat plane, but I can't have a flat face, right? So that's something that I try to incorporate over here using these two measures or these two score values.
So
and
Kevin,
I do this.
May I ask? This is Christine. So you say the face, it's not okay if a face is missing, a part of the face, but it's okay if the torso is missing. Wouldn't this be context dependent? I mean, game dependent, objective dependent, or are you just trying to do this for any kind of mesh? I mean,
this is for any kind of mesh in a general open or general human mesh, not really for any other, but human mesh.
Any kind of human mesh. But then why torso is okay to be partially there versus the face then?
No. I didn't mean it's partially there. I meant if it is a flat region,
captured,
right? Yeah, if it is captured as a flat plane, meaning if I don't have variations in the mesh, right? There are some meshing techniques which would smooth the mesh, right? Which would basically reduce the overhead or the number of points. So the whole idea is that's what I'm going to go with the next part of the network adaptive mesh. But if we have thousands and thousands of points, then it's going to be really heavy, right? So what some meshing techniques do is they try to reduce the quality or reduce the number of points. And if you do that, you are going to end up with, let's say if I have only 4 points, 1 point here, 1 point here, and then 2 points below, right? So the mesh is going to be just 2 triangles, and it's going to be a flat surface. But for my torso, it's still fine, because generally a torso region is not really, there is not a lot of variation. Well, there is, but I'm not saying there's not. But it's fine if we have less number of points and we can determine, or we can have a flatter region. We still want to have a complete thing. I mean, the overall part is considering the triangles and the holes. We don't want holes. We don't want partial body. It's all about how important the part is. For face, I can't just have 4 points, because if I do that, it's going to be a flat surface. That was my context over here. But I don't think so it has anything to do with games, because we are not really interacting with the mesh. We are interacting with the skeleton. This is more about the visual aspect of it. How good do I look in the game versus, not versus, but how appealing does it look in terms of the of my mesh?
So you're interested in having some fidelity of the graphics of the face versus low resolution. I mean, in some contexts it may not matter. In some games or whatever you're trying to do, it may not matter whether you have a high fidelity of the face.
So I would say that is a completely, if I'm trying to, so let me answer it in a different way. So I agree with you. In some games, it's not going to matter if we have good face or not. What is going to matter is how good the interactions are, how well I'm interacting with the objects.
Right.
But even in those games, it's not going to matter how good my torso is, how good my face is. So those two are separate concepts in a sense that what is the type of quality that we are trying to address? So that is about the interaction aspect versus the visual aspect. Over here, all I'm considering is the visual aspect.
Okay.
I'm not worried about the interaction aspect over here. But that's correct. I agree with you. Okay. And that's where I'm going to the next part below. That's what I did is
Okay.
Does the visual aspect only matter? Because most of the systems, they would train, or they would see, or they would try to get the visual quality as high as possible. But that's not the only thing. If you don't have proper interactions, it's not going to matter. I completely agree with you over there.
Correct. Okay, thank you.
So yeah, in this visual quality aspect, I just divided it into the holistic part and the local part-based part. And the whole motivation over here was, well, I mean, I would not say this is not the motivation, but the motivation was to compute an objective score using subjective feedback from the users, right? So what I mean, I would say it's a well, this is a very old work, so I can say this has been done, or I can improve it a lot now. But the whole idea over here was to use the user ratings and learn some weights for what all parts of the body are more important, right? I mean, I just gave you the answer that face is more important than the torso, but that was probably learned from the user study that I did, and in terms of what all things are important, what all factors are important. I just incorporated different factors that I felt could be part of it. What not I, but like some of the other people I consulted felt could be part of the quality, and I used that and in a user study, and we just learned those weights. But this was just about quantifying it in an objective sense. But we are still not considering the fact that what about the network, right? I mean, I'm just saying, if I have a mesh, what is the quality? But what if I cannot even get this kind of a mesh, depending on the network, right? So if you have network bandwidth, which is like a low network bandwidth, what's going to happen, right? So that's something that I wanted to address, at least in terms of the application that we were developing. We wanted to do something, we wanted to have a setup where we could adapt to the network. Plus, more importantly, we wanted to have a setup is we want to try to reduce the amount of data that is transmitted. Yeah. So generally, I would have a 0.2, 0.5 megabyte of depth data, 2 megabytes of colored information, and then you would, I mean, I would say 30 FPS, but let's say minimum at 10 FPS. Right? We would need approximately 150 megabits per second, which is extremely high. Well, I mean, not in current days, but it's still high that I would want to transmit this much information. Now consider if 10 of us are in a commerce shared scenario, right? It's going to be exponential if we are sharing this information back and forth. Yeah. So we would want to try to reduce this in some way. So the strategy that I mean, it's just network, not really network. It's just the system arrangement. This is more about the system arrangement, what I did, right? So what people used to do, or even we used to do before, we generate the mesh and we transmit the mesh, right? And mesh adds up some information, right? So we reduce that by just doing meshing on the receiver end, where the receiver is going to handle all the meshing part, depending on what the data is received. That's just a common sense thing, but that was not being done, and we just did that. But the more important part about it is how can we reduce the number of points efficiently, right? We want to reduce the number of points when we want to reduce the number of or the size of the data. So what I did is we reduced the data size to about, even if we reduce it to 1,000 points, and 1,000 points corresponds to doing 5 kilobytes plus 10 kilobytes of color image. We do JPEG compression. We reduce it down to about 1.2 megabits per second compared to 150 megabits per second. Right? That's what we generally we did by doing two things, by doing some minor bit level manipulation. So we did bit level encoding of the 3D points compared to just sending floating point values, plus the pixel quality of how we are going to select those points. Yeah. So it's talking about pixel quality, right? So again, a rough idea or a rough overview of what is happening is we have the depth image. What we do is we take the X and Y gradient information, and using the X and Y gradient information, we try to estimate the quality of pixel, or the importance of a pixel in a sense, quality or the importance of that pixel. Now using that, we try to do a shape preserving selection, meaning we want to have our silhouette. That's the primary thing that we want to have, first point. Yeah, so that's the first thing that we do. We use a silhouette and edge detection based technique on the depth image to try to extract the silhouette, and using the silhouette, we try to do there's this shape preserving selection from this, or for all the pixels that we have calculated. So this is what we get. Now, this is the minimum thing that we think we need to transmit, but we may even add more points if the network allows us to do so, right? So what we do is we try to add more fine details depending on the parts. This is where the parts comes in, right? So as I said, if you just have less number of points in the torso, it's not going to matter that much. But that's not really that's not really true for everything. I agree with you, right? So if I'm saying it from the side view, obviously I need variations in this part of the body. It's fine if I don't have variation over here. It's fine if I don't have a lot of variations over here, but I need for this hand portion and the face portion. But that's all going to be controlled using this quality per pixel, using this gradient information. So it's not really just part based, but we try to give some motivation or some idea that some parts are important, and using those parts let me put it this way. Variations in some part of the body is important, and we would want to have more number of points over there. Now, if you just saw over here, this is this person's shorts, right? I mean, since the shorts are black and the way it's captured, it is having many points compared to this. It's saying that there is a lot of variation over here, which was not needed. And that's all dependent on how this gradient information was calculated. So it's not just directly part based. Yeah. So these were some of the results. I'm showing you in terms of a perspective that this was 15,000 points and 100% JPEG. And if you see it from in the same view, but it's now 1,000 points, so reduce it by a factor of 15, and the JPEG quality is also reduced from 100% to 30%. We are still not having a lot of difference, in a sense that the visual quality is not really different compared to this with this, considering the objective quality matter, or the measure that we had. Same goes with these two, 15,000 versus 10,000. So essentially, we were trying, we could reduce about, this is not a compression strategy, but in a sense, it's compression, as we are reducing the amount of data that we are transmitting, right? So that's what we did, non-compression based reduction in the data. Yep. So this is good. We can have this. We can have the reduced quality that could look fine. But there's still problems. Obviously, the open mesh part, right? So we would want to try to close this mesh. Yeah. For that, we need multiple cameras. We can't just have one camera. Or if I have one camera, I just generate the complete 3D model in beforehand or progressively. But there is a lot more computation aspect involved over there. Many other aspects which I didn't dive into. I went into the other part of it where we have multiple cameras and try to fuse those camera information. So before we go on using multiple cameras, we need to calibrate. So checkerboard calibration method, which everybody in computer vision knows, it's probably one of the best known strategy, and everybody uses that strategy, which is good. I'm not denying the fact that it's not good, but for our use case, there's a lot of problems. As you saw, there's like 7 different cameras, and I may add more cameras. I may delete or remove some cameras, and I may even move this pole over here. And it's very easy to move a pole by just walking by next to it, right? So it's very easy to move these stuff. So, and it was not really, the checkerboard pattern takes a lot of time because you have to do pair-based or pair-wise calibration. You can just update the code to do combined stuff, but it needs to view on a plane-based system, right? Which is not really advantageous completely in this use case. So what I kind of did is we had the skeleton. I know the skeleton is not really accurate because it's a Kinect skeleton, but it's still accurate enough. So what I could do is take those skeletal information and try to do a calibration using skeletal information. So using direct 3D points obtained from the skeleton joints and use that to compute the calibration strategy or the calibration matrix, the transformation matrix. So that was the general idea. And the advantage or the motivation, again, the other motivation is it is extremely fast, right? So 7 cameras, it's extremely fast to calibrate them. Just walk around, as you saw the other person, he was just walking around in the scene, and all the cameras would be calibrated, right? So just walk around like probably a few seconds or a minute or so, and all the cameras can be calibrated simultaneously. Obviously, you have to consider the aspects, right? So what all joints we should consider? We should do skeletal flipping because Kinect cannot determine front versus back, right? So we need to tell the skeleton system or our code that, like this is front or this is back. Plus, we would also want to have some constraints. Even if let's say this person is just standing over there while calibrating, that is not advantageous, right? We would want to have, like a calibration as a motion-based or spatial calibration. So considering these 3 constraints, we have the temporal constraint, meaning we don't want to take every point. We would want to have at least 15 millisecond worth of difference because we can't really walk much within that particular time interval. Plus the motion constraint that we would want to have consecutive motion less than certain amount, but more than certain amount as well. Meaning we would, if there are 2 frames that I'm trying to use, if the motion is very high, it would be jittery, or not jittery, but it would be in a way that the front camera may have captured it properly in the correct timestamp, but the back camera may not have been able to capture that in the correct timestamp, right? So we want to have all of those constraints depending on there's different hardware constraints, but specifically in this case, it is for Kinect, but it's still in a sense generic for systems which can capture skeleton data at 30 frames per second. Right, so once we have the calibration, you would want to generate a combined skeleton from multiple cameras and combined 3D model. So this is just a standard setup where we have cameras connected to individual machines and individual point clouds and skeletons being captured. Now, the whole idea of how to combine the skeleton or create the 3D model or 3D point cloud, not really 3D mesh that I'm doing 3D point cloud, is using a consensus approach where I'm assigning a probability or a score value for each joint. It's not really a probability. In a sense, it is a probability, but it's basically a score value for each joint where we have scores from multiple cameras, right? So let's say this is 4 cameras. We get the skeleton from all 4 cameras and we associate some probability of those joints. And that is dependent on multiple aspects. One aspect is the angle in which the person is looking at. The other aspect is, or angle from the person and the camera. The other aspect is the joints, the joint angles, how the joint angles are moving and what specific joints are there. All of these, I mean, if it's facing in front or back, all of those aspects are going to be considered in terms of figuring out whether that joint is accurately detected by that particular skeleton or that particular camera or not. So there's definitely advantage in creating a combined skeleton over just using one camera skeleton. As it's evident, I just tested it out in a simple game where I had multiple users try to play this game using a single camera skeleton versus a multiple camera skeleton. And the score was obviously higher in terms of the way the people interacted with these virtual bubbles. And the last part, what I worked on, which is like most recent one, I still have to do some bit more work to improve this strategy, but the idea is, can we automatically assess the task performance? So as what Christine mentioned, we have different qualities that we consider, right? So we should not always just focus on the visual aspect. So visual aspect is one thing. There is immersion aspect, how immersed you feel in the game. There is the interaction aspect, how interactive. So if there is X amount of interaction, are you able to achieve? Is your game able to achieve that much amount of interaction? And people are able to effectively interact with the virtual objects and play the game successfully, right? So that is the interaction aspect. The other aspect, whenever I'm talking about serious games, because that's what my focus is, we would want to assess the task performance, right? So the task quality in a sense, whether the user is able to perform a task efficiently or not in terms of the actual outcome, right? So serious games almost always have actual outcomes, right? So we want to have an actual outcome comparison in a sense that how the task performance or how the user is performing that task. So I came up with a modeling strategy where there's a model, hierarchical task network, HTN, which is mainly used for robotics and different aspects, different modeling aspects. But I kind of try to extract that and try to extend it or augment it to create an augmented HTN for assessing the task quality of any task whenever the task is being played. Right. So there's two key aspects which should be considered. One is how the task assessment is done and who is being assessed. I would say this one is fairly straightforward in a sense that I can assess single user, I can do a group user evaluation, or I can do individual from the multiple users in the group, right? I think this is more of the, is just selecting who you want to evaluate. But the more important part is how can you evaluate it automatically, right? So I was doing this already in some extent for the, let's say the exercise games, right? So we already have the recorded information from the therapist. Can we compare the recorded information from the therapist with the task performance of the user and give them direct feedback? Yeah. So direct performance, direct feedback, and because of that, or considering or doing it that way, what we call it as an action level assessment. Right? So we are performing an action and we are comparing that complete action. That is what is known as an action level assessment. We want to assess the trajectory of the motion. The other aspect, what I considered was there are some things where you're moving the virtual objects, right? So let's say in the hydrometer game, I'm picking up the object and I'm just moving that object, right? So I have to consider the aspect of the object, how those objects are manipulated. Those are the task level manipulations versus the action level manipulations. And that is the thing that I incorporated, and we can do automatic. Well, it's obviously you need some reference, but the expert, so the subject matter expert can provide that reference, and using that reference, we can do automatic evaluation or automatic assessment within any game or within such games, serious games. I would not say any game because that's a wide domain, but within such serious games. Yep. So an example was the hydrometer experiment where we have to divide it into subtasks, right? So there's 4 tasks that are involved in this experiment. We have to pick the hydrometer. Once you pick it, you have to move it to the cylinder. But while you're moving, you have to make sure the hand is in a certain, it is basically picked up from the top. It is in a certain angle. You cannot pick the hydrometer like this because obviously you transfer oil and it's not going to work properly. It has to be picked up from the top. So all of those things can be incorporated directly using the subject matter expert's feedback. And once incorporated, we can do automated assessment by just comparing the values or comparing the positions of the 3D objects present in the game. And we try to do an objective, an evaluation of that, where the instructor provided some scores and the system provided some scores, and we compared that, correlated that, obviously not a direct comparison, but a correlation between the individual tasks and the overall score. The correlation for the overall score was about 91%, 90%, and so on. And more importantly than this correlation, because it was a small study, right? I mean, we still need to do a bigger study where we have more than one experiment, and whether this strategy forwards it along multiple experiments or not. But more importantly, the instructor's workload is reduced a lot, and the system is able to effectively score the user performance. And which, in fact, in this case, it was doing fine. But we're probably going to have more studies or more experiments set up for this particular purpose. The other part was about the Exergame. It's still a serious game, right? So we can represent that as a IA-HTN again and do the assessment of the particular person, right? So it's basically about all those bubbles popping up. This was like very straightforward. It's nothing too fancy, but in terms of this assessment, there's two key aspects. One is the bubble part, and the other is the anomalous movements parts, where the person needs to, if the person is not moving some parts of the joints, or if the person is moving some other parts of the joints that it should not be moving, or the person is falling, all of this can be incorporated using the recording of the skeleton or recording of the therapist. Yeah, this was some numbers from this experiment, from this particular study. And in terms of the anomalies detected, the repetitions, bubbles hit. And we also did some analysis on the trend of how the person was improving or not between multiple days, right? And we did a study with Dallas Veterans Affairs where we basically got 10 patients, but a couple of them dropped off. These were all actual patients with disabilities, with stroke, and they were suffering, and some people could not finish it. Some people had to go back to the in-person therapy or something like that. But there are issues with that, and we can try to see if over a period of 1 month whether they were able to continuously improve their performance or not. Right. So this is basically about a complete picture of what I have done and what I've what my general focus of my research is along the lines of interactive 3D tele-immersion and with respect to serious games. Right. So this was basically these were all the publications that I had or that I have in progress, and some ongoing research. Right. So I just wanted to put this over here just to give a feed or like a sense of how we can go forward with this. Obviously, nothing is completely solved in research, right? So there's a lot of aspects within the computer vision domain. The first aspect that I am doing right now, that I'm working on right now, is the hand pose estimation. So in all of these, I mean, we saw this hydrometer. We were using a leap motion because of the leap motion is like very closer to the camera. It is detecting the hand properly. But what I want to do is not use leap motion, rather just use Kinect, or rather just use one camera which is sitting somewhere and it's capturing your entire body. But while capturing your entire body, it is also able to capture your hands, right? And this is a domain which many want, but it's not being researched so much. I mean, I would say not even so much. It's not being researched. It's a very shallow field of research right now, because of the way how data is being captured. There is not a lot of data over here. And now almost everybody in computer vision is either doing deep learning, right? So deep learning, we don't have much data to do this hand pose estimation at distance. Going forward, do gesture recognition and emotion recognition that can be helpful to do, like in this serious games. Apart from that, bit more computer vision-y stuff is about detecting the stereo images or detecting or removing uneven lights from the stereo data and creating stereo images from, creating disparity map from stereo data efficiently. Posture analysis is something we have the pose. We want to do the posture analysis in a sense that if the person is performing this exercise, whether that exercise is being performed in a correct posture or not, right? So not the pose, but the posture. The posture is important. And while doing this for multiple days, right? So generally this is going to be done for a longer duration, maybe a month, right? So over a month, is the patient improving or is the patient degrading, right? So those are the things that the posture can be analyzed, and there can be some suggestions given by the posture showing whether that particular person is improving or not. And this is an offshoot, which is like a small thing that I'm working with another faculty, where we want to do 3D scene reconstruction from drones. We have UAVs, and we can try to do 3D scene reconstruction. because I mean, there are a lot of people who are doing this. In terms of the AR/VR aspect, as I said, I kind of live in both of these domains. But in the AR/VR aspect, I want to expand the serious games and try to get more on the evaluation aspect of chemistry lab and these exergames. Exergames, I've already started the actual studies with patients, and we want to extend that more as well. But the chemistry lab, we want to do a bit more along the aspect of learning, right? So can we deploy this, and can we have a bit more learning aspect, and can we have it more generalized? And chemistry is something that I focused on, but it could be any other laboratory setting. But chemistry is something which is easy to like start off with. And task performance assessment and doing virtual assistance using gesture recognition and motion recognition with cognitive intelligence incorporated with it. And so these are some ongoing and future research interests that I'm working on, and I'm planning to work on. I would happy to hear from you guys if you have any comments or ideas or suggestions that could probably help me. Maybe also could lead to like a collaborative aspect. Right? I don't know. Did I finish early or late? Oh, okay, a little bit early. But yeah, I mean, thank you so much for having me here, and thank you so much for listening to the presentation. If you have any questions, please feel free to ask.
Thank you very much for the very interesting talk. It's also so many, your projects. So now I think if anyone has some questions, I'm pretty sure Dr. Desai will be, pleased to answer them.
I have a question.
Yes.
Thank you for your presentation. I would like to know how you communicate with the subject matter experts to know what type of interactions will actually make sense, and how to evaluate them, and yeah.
Yeah. So so subject matter experts. There's two aspects. I've tried one of them, which basically what we want to do is we want to have. It's still not 100%. I would say 100% automatic, but the game developer, I would not say game developer, the game designer, which is basically going to create a, what I have is basically I have I would say a system or multiple scripts in a sense, if you're using Unity, but basically multiple scripts in a sense where I can have some drop-down options for the expert to decide on what they want to do. Obviously, the first part is if they have to, like develop this particular game for, let's say, hydrometer, they need to, like I need to communicate with them. I need to get their input on what is the thing that they want, right? So all of that once we have, but the evaluation aspect is what I'm mentioning about, is they can do a drop-down based scenario where everything is there. They just have to select what is of importance in this particular, or how many things that they want the user to be evaluated with. And based on that, they want to have, they want to select what is that they want to do. If they want to also record, I also have the option that they can record themselves, and the recording is going to be used. Once they record, they're going to select whatever joints they're considering for this recording. And those joints are basically going to be assessed against the live performance, right? So let's say if I'm playing, or if I'm doing an exercise for hip abduction, I've recorded myself and I'm marking that these are the joints that I want them to move. These are the joints that I want them to stay steady. And I'm going to use that. The code is using that internally, and it's basically going to evaluate or compare against those joints. I don't know if this answers your question. I'm hoping this was the question.
Yeah, thank you.
Yeah.
Any more questions? Great, thank you very much. Thank you for Desai for your time and your valuable contribution here today. So if we don't have more questions, let's just warm thanks to the Dr. Desai for the presentation today, and also I want to thank everyone for attending this seminar today, and I hope everyone has a nice weekend.
Yeah, thank you so much, everyone, and thank you so much for your time and inviting me. And again, if you have any questions or any feedback, suggestions, any collaboration ideas, feel free to send me an email and we can discuss.
Thank you so much, Kevin.
Thank you.
Thank you.